the paper Data-Driven Design and Evaluation of SMT Meta-Solving Strategies, Balancing Performance, Accuracy, and Cost. The paper was originally presented at the Automated Software Engineering Conference 2021, and we received a Distinguished Paper Award for that, and it's joint work with Falk Howar. What we do in the paper is we talk a little bit about on how to combine different SMT solvers to form meta-solving strategies. And I will highlight some parts of the paper, which are solver combination patterns. Then I will talk about how we process different existing string theory benchmarks in the literature and how we computed all the necessary metadata to run experiments and to compare performance on that. And at the end, I will talk shortly on evaluation of different SMT meta-solving strategies and how we use these presented patterns in the context of SMT solving. Why do we care about meta-solving strategies? The answer is normally we talk about software verifiers if we go to conferences, and software verifiers, at least these we work with, work the way that we have software and then we have a property, and the software verifier combines the software and the property into an SMT problem. And then the verifier works in the way that internally it asks an SMT solver whether the converted SMT problem is satisfiable or not, and these satisfiability decisions directly influence whether the software verifier is able to prove or disprove a property on a software problem. And in the consequence, the verifier performance is really tightly coupled to the SMT solver. And what we have learned early is that if we exchange the SMT solver, the verifier gets better or worse. And the resulting question for us is how can we combine different SMT solvers into what we call a SMT meta-solving strategy to get a reliable constant performance that's close to the best possible performance for the verifier without depending heavily on a single SMT solver. And we have been especially interested in doing these SMT meta-solving strategies in the context of the string subtheory in the SMT area. So all I'm going to present in the following is evaluated on string benchmarks. The first thing we did is we collected available benchmarks in literature, and when we looked a little bit more detailed into existing work and also into existing performance evaluation, what we saw multiple times are really close-looking problems. So here on the left and the right, we see two instances we found in a benchmark, and the only difference is that the variables have different names. In the context of an SMT problem, the variable name shouldn't be actually influencing the performance of an SMT solver. And I showed a little bit in the bottom here, we have found 373 instances of this very same problem. It's taken from the Calusa benchmark, which is really famous for evaluating SMT string theory solvers. The Calusa benchmark contains roughly around 35,000 tasks, if I'm not mistaken here. And SMT solvers and new SMT solvers are used to be evaluated on this benchmark. And if we re-evaluate the same solver on multiple instances of the same task, it's a little bit hard to tell at the end what's the difference between two solvers if they perform kind of similar, except for a couple hundred tasks. So what we implemented is a duplicate detection, and we cleaned up the benchmark a little bit. And what we contained is a benchmark set that's significantly smaller. So it just has like 17,701 tasks. And while it's smaller, we can make sure that for the given described metric, all of them are unique, and we don't have these duplicates anymore. And the next thing we need is a correct result. So often the tasks are presented in literature as instances collected somewhere during analyzing a problem, but there isn't what we call a ground truth label saying, okay, we have this task collected, we expect it to be true, or we have this task collected, we expect it to be unsatisfiable. And what we did here is we used a set of different SMT solvers. So in the comparison, we used ABC, CVC4, set3 with the sequential backend, which is the original set3 string solving backend. And then there are two extensions to set3 that are called set3 string 3, which is also available for selection in the current set3 binaries. And then the more new set3 string 4 solver that's recently introduced in the second half of last year. And we also use Princess and Ostrich. Ostrich is built within the Princess framework. as a string theory solver. And now we try to compute ground truth labels, and we did it the way that for SMT problems that are satisfiable, we used a Java wrapping library, JConstraints, which is also maintained in our group, to verify the maintained models. So the SMT solver says, okay, this is a satisfiable problem, and to prove that it's satisfiable, I give you a model. We can take the model, put it into the original SMT problem, and verify that it's actually satisfiable given the SMT semantics. And that's what we did for satisfiable tasks. And then we used CVC4 and SET3 to confirm the obtained models in the Java library. And for unsatisfiable tasks, we used majority voting. So we solved tasks with all of these solvers. And then we take the majority vote for an unsatisfiable task as the ground truth label, unless we have found a satisfiable counterexample that could be confirmed, which was actually never the case in this data set. What we find out is on the clean benchmark set, CVC4 is truly the leading solver in this case. It solved 70,020 tasks. We don't see any incorrect results, and we also haven't seen any unknown results, which would be the case if an SMT solver gives up on a task. But we do see 260 errors where somehow CVC4 crashed in the benchmarking process, and we have seen 421 timeouts. All of these experiments have been run giving an SMT solver a single core, 2.5 GB RAM, and 5 minutes time limit. And the second best solver was SET3 sequential on its own with 16,117 solved tasks. We have seen 2 incorrect results and 1 unknown task, but also like 1,500 timeouts. And then the next best solvers, more or less, are SET3, string 4, and ABC. We see like 14,000 and 12,000 solved tasks correctly, but here we also see a huge amount of incorrect tasks, and that's where accuracy comes into play. So if we have an SMT problem and we solve it, we actually want to be that the result is reliable. And in this case, we could observe that ABC and SET3 string 4, while giving a lot of answers, don't always give the correct answer, at least for unsatisfiable problems. So next we iterated on how could we improve that. And what we propose are solver combination patterns to combine these multiple SMT solvers into one solving backend, what we call a meta-solving strategy, that allows us to play between investing more compute time to get better results or to get faster results and more results eventually. So we have found in literature that works with SMT solvers different patterns. On the most left, we see a majority vote pattern where we just run all solvers for a given resource limit, and then we do a majority vote on the obtained result to get the final verdict. That's basically what we used in the unsatisfiable cases to contain a ground truth label. The second pattern is called the earliest verdict attempt. It's often recommended in literature, so you just take all available SMT solvers, then you start them all in parallel, and you just take the first returning SMT solver as the final verdict, and it's supposed to be way more performant in terms of it solves more problems faster, but you have to invest more CPU time to do that. And the next problem is what we call the verdict-based second attempt or validation strategy, where we have an SMT solver that computes the verdict, and then we integrate something that's checking the verdict, and based on the result of the check, we either accept it, or we call another SMT solver for cross-checking, or we hand off the problem completely to another SMT solver. And on the very right, we see a feature-based selection pattern where we analyze the problem in upfront, and based on the result of the analysis, we select which SMT solver is going to solve the problem for us. So that's these are general patterns we see for combining SMT solvers. And the question is now, what do we get from applying these patterns? And what we have done is we did a mixture between implementing the patterns and simulating what we expect them to achieve. So for the earliest and the earliest trusted strategy, we just have run simulations given the results we often collected from the 7 solvers. And CVC sequential course and CVC sec evil are 2 strategies we actually implemented in JConstraints. And these are instances of feature-based second attempt pattern. And collected the data while running them actually. So, and what we see here is if we take all the data available and we implement an earlier strategy, we would expect in total to get like 70,255 correct results, which is a little bit better than CVC on its own. We see that the CPU time would be more or less the same. It's a little bit faster than CVC4 on its own, even if we run all the solvers in parallel. So we computed that by assuming that the fastest returning solver is like the CPU time invested, and then we multiplied it by 7 to get an estimate for how expensive the strategy would be in the best case. But what we also found, what we don't want is actually these 400 incorrect results. So we looked a little bit more in detail into the results, where they're coming from. And what we found is that what we've seen before, the incorrect results from ABC and set 3 string 4 are influencing the earlier strategy, as these two solvers are typically quite fast. So what we have done is this earlier trusted strategy, where we did a pre-selection on the solvers we trust, and we have seen that ABC and set 3 string 4 have some weaknesses in unsatisfiable cases, so we excluded these solvers for unsatisfiable cases. So it's a kind of pre-filtering of the earliest strategy. And we see we can actually increase the correct answers, but now we also get 247 unknown cases, but just 5 incorrect cases. This is eventually better, so the performance gets better and the accuracy gets better, but we also pay way more CPU time in this case. And what we found works best for the use case we actually have in the verifiers is that we ask one solver, and then we analyze the result and eventually ask a second solver. So in the CVC sequential core strategy, we ask CVC4 with a time limit of 1 minute, and if CVC4 comes up with a result, we validated the satisfiable results by analyzing the model, and we validated in the core strategy also the unsatisfiable results by extracting the unsatisfiable core and giving it to set 3, which was the second solver involved in the strategy. And we see this way we can solve 60,953 tasks, but all these verdicts are also cross-checked. So if a solver says it's unsatisfiable, then other solver has to confirm it. We see 37 tasks are unknown, but we don't get any incorrect results, and the CPU time is comparable to running CVC4 or set 3 on its own in the backend, so it's okay for us. If we don't do cross-checking on the unanswered results, we actually get 17,290 correct tasks, which is better than CVC4 on its own, but we have also seen 2 incorrect results, which is not totally what we want in the end. So we actually get a higher accuracy if you also do unanswered core checking here. And that said, these are our findings, and all these are the meta strategies, how we use them in verifiers today. And the study showed that it's really crucial to look a little bit more detailed on the SMT solvers, but all the data and experiments are built with current software commits, more or less from ongoing development projects. So if you rerun it today, it might be totally different. So especially these incorrect results are not like general valid. That's like what we found for the versions we worked with beginning last year. So we have run it a year ago. It might look totally different today. So we have to rerun these kinds of analyses frequently to maintain good meta solving strategies for our verifiers. And these are the main contributions we made in the paper. You will also find a short discussion on how to analyze different involved features in the SMT problem for a feature-based solver selection as well. Thank you. I'm happy to answer questions.